Hello guys, so my name is Abhimanyu Reddy and my serial number is 17. My registration number is 18BEC0274 and this is a video regarding computer organization and architecture digital assignment 2. So this assignment is regarding taking a journal paper regarding floating points. So I've chosen the paper floating point unit using error correction scheme and modified anticipator. So let's get to the first question. So the first question is about explaining how the selected papers is related to the COA syllabus or curriculum that's been going on right now. So this paper presents architecture for user-defined floating point, that is addition or subtraction unit with modified leading zero anticipator, that is LZA. So in floating point addition, unit adder normalization unit decides the critical path delay. So predicting the shift amount before the adder output helps in reducing the delay that is introduced by the normalization. So the proposed error detection logic is implemented in this in parallel with the adder and taking inputs from LSA. So with this proposed method, we can achieve the reduction in the delay by 18.98%. So when compared with the conventional floating point unit, so there is a decrease in time, that is a delay of 18.98%, and the proposed error detection and the correction method also reduces the error occurrence possibility in the obtained results. Now, getting to the second question, this is the existing architecture that's been edited in the software in an encapsulated PostScript in the that is there in the paper, and this draw the tab. The third question is drawing the tabulated results and graphs using the Office suite in encapsulated file format. So the proposed LZA with error detection algorithm described is implemented in this, and the results are obtained. So conventional design with proposed scheme is implemented in the Verilog HDL, and the simulation in this is done using Xilinx ISE Design Suite 13.1. The device used is XE6SL-X4 of Spartan 6 family. The comparison of the conventional design and the design with the proposed LZA and error detection is there in this table on the basis of LUTs and the part delay. So the results are shown in table 1. So this is the table 1. This is the LUTs and this is the part delay. These are the conventional unit timings and these are the proposed design timings. So the comparison of the proposed design in conventional design discussed is shown in the table 2. In table 2, the comparison is based on the shifting done, proposed method computing the shifting amount along with the adder output, and also the normalized time required, and it's also based on the availability of error detection scheme. So this is the comparison of floating point units. So shifting amount, normalization time, and error detection. So in conventional unit, it is obtained after the adder output, and the normalization time is requiring more time, and the error detection is not available in this. Whereas in proposed unit, the obtained it's obtained along with the adder output, and it also requires less time, and it detects the error prior to the LZA and the adder output as error correction circuit in parallel. So in this design unit, the modified leading zero anticipator and parallel error detection technique is proposed. So this requires less time and detects error in advance with a little overhead of area over conventional circuit. So this is the proposed architecture that is discussed in the paper, which helps in reducing the part delay by 18.98%. And this is the transistor level internal diagrams using electronic schematic capture. The sixth question is regarding comparing the proposed architecture with the existing architecture in our reference books. The floating point is basically based upon the encoding of binary information in the charge configuration with quantum dot cells. And also, there are two electrons in floating point, a cell that can tunnel between the dots inside the cell. The electrons must be located on the opposite corners of the square according to the Coulomb repulsion in ground states. So, an arithmetic logic unit, a multi-operation combinational digital function. It can perform a set of basic arithmetic operations and a set of logic operations too. The ALU has three selection lines to select a particular operation in the unit, and basically FPU and FXU execute instructions concurrently. So FPU and FXU share instruction buses. FPU and FXU synchronize on all interruptible operations. Decoupled FPU and FXU execution units, they avoid the interlocks, and register renaming and to data queue is also being done in that. So coming to the advantages of the proposed design over the existing design that we are using now, is that the proposed LSA with error detection algorithm described is implemented. So the conventional design and the design with the proposed scheme is implemented in the Verilog HDL, and the simulation is done using the Silence ISA as we have talked before. Uh, so this is the latest software, and in design unit, the modified leading zero anticipator and parallel error detection technique is proposed. So with this, the proposed unit requires less time and detects error in advance before the anticipator. This method outputs the result really fast, and it will not even affect the course shifter when the output is ready. So therefore here the time gap between the error detection blocks output and the course shifter output is reduced to minimize the area. Coming to the merits and demerits of the proposed and the existing techniques hardware, so let's just discuss the merits right now. The proposed approach enables parallel execution of conventional LZA and its error detection. So the error indication signal can be generated earlier in the stage of normalization. So this reduces the critical path and improving the overall performance. And the circuit implementation of this algorithm also shows the advantages of area and power compared with the previous work. This method proposed uses 1-bit MSB or sum obtained from the adder. So even if the proposed error detection scheme takes input from adder, it does not affect the latency as it does not come into the critical path. So coming to some of the demerits, some of the areas which could be worked on is the large precision, complexity of design, bit cancel management, complex rounding process are some of the demerits. The only demerits of the proposed design yet faced is that it would be expensive to unroll into hardware environment. And unfortunately, in predicting the shift amount by conventional LZD design, the result could be off by one position. And the applications of the proposed design are some of the following. That is, most of the available algorithms are inexact in nature. They predict the shift amount with a possible error of 1 bit. The proposed error detection logic is implemented in parallel with adder taking input from the LZA. So with this proposed method, we can achieve the reduction in the delay by 18.98% as we have discussed before when compared with the conventional floating point unit. Also, the proposed error detection and correction method reduces the error occurrence possibility in the result obtained. So this is the flow chart or the algorithm of the transistor level circuit. It consists of the comparator, subtractor, the mux, the swap, the shifter, the adder and the subtractor, the normalization, and the exponential adjust. So all these block diagrams have been drawn using the online tool draw.io. So this is one of the proof of me drawing one of the block diagram. So this is the block diagram of the existing architecture that I have drawn using draw.io. So yeah, that is that.